Alright, so my stream died, but I think I'm back now at a new link. Gonna Alright, let me just check. Okay, I am live for real this time. Problem just dropped. Oop, I want to mute that. Alright. Nope, don't want to hear myself. Well, I think I'm live on my channel. Just gonna verify this before I get started.
I am Sam, and
cool. I am live. Harry's back. Sweet. All right, day 25. Something. The room key is a small RFID card. Finally reach the door to your room, swipe your card, and beep, the light turns red. Phone number for tech support. I don't want to go back down the stairs to the front desk. So instead, what am I doing here? Transforms a subject number. To transform a subject number, so we're stepping into the cryptographic handshake. To transform a subject number, start with the value 1. Then a number of times called the loop size, perform the following steps. Set the value to the value multiplied by the subject number. Set the value to the remainder after dividing the value by 2020-1227. Weird number. The card always uses a specific secret loop size. The door always uses a different secret loop size. It's prime. That's interesting. Something to note. Cryptographic handshake works like this. Card transformed the subject number of 7 according to the card's secret loop size. The result is the card's public key. Oh my god. Cool. The door transforms the subject number of 7 according to the door's secret loop size. The result is called the door's public key. The card and door use the wireless RFID signal to transmit the two public keys to the other device. They exchange. Now the card has the door's public key and the door has the card's public key. Because you can eavesdrop on the signal, you have both public keys but neither device's loop size, which I guess is sort of like the private key here. The card transforms the subject number of the door's public key according to the card's loop size. The result is the encryption key. The door transforms the subject number of the card's public key according to the door's loop size. The result is the same encryption key that the card calculated. If you can use the two public keys to determine each device's loop size. Why do I have day 23 up here? Getting distracted. If you can use the two public keys to determine each device's loop size, you will have enough information to calculate the secret encryption key that the card and the door use to communicate. This would let you send the unlock command directly to the door. For example, suppose you know that the card's public key is this number. With a little trial and error, you can work out that the card's loop size must be 8 because transforming the initial subject number of 7 with a loop size of 8 produces that. Then suppose you know that the door's public key is this. By the same process, that door's loop size is 11. At this point, you can use either device's loop size with the other device's public key to calculate the encryption key. Transforming the subject number, this is the door's public key, with a loop size of 8 produces the encryption key, which is that. Transforming the subject with 11 also does that. What encryption key is the handshake trying to establish? Okay, are these the, what are these inputs? Oh, I have the public keys of both. Okay, I have the public keys of both items. So I use the public key to figure out the loop size. So I get my public keys, I transform keys, or one key anyway, into loop size. Then I or sort of reverse that. I brute force it, and then I transform using loop size and other. I transform the other public key using this loop size that I found to get encryption key. Okay. I don't think that it matters which is which. Yeah, I don't think it actually matters. Okay. Okay, this should build so far. Oop. This should build so far. Nice. Of course, I'm wrong on that. I have to say, this part 1 does not seem that hard, but part 2, I bet, could be quite difficult. But that builds. Okay. So then I want to get the loop size of, say, the door public key. Door loop size equal get loop size. We start with 7, and we want to end up at the door public key. Okay, let's define get loop size. Start is a U64, and target is also. Okay, so the what's going on here? 1 second. Loop size is 0. And then wait, subject number. Oh, okay, this is the subject. Start with 1. Num is 1. Then the loop size we will, while num is not target, num is, we multiply by the subject number, and then, and then we set it to the remainder after dividing by this prime number that starts with 2020. That should all be positive. and then increment loop size. Let's check that this builds. Oh, we gotta return the loop size as a U64. Okay, so then we got our doors loop size. So then we also just want to write a straightforward implementation of transform. So that's just to loop size. We do this. Multiply by subject number. So because these are both prime, there's, yeah, whatever. Okay, so then what we want to do here is we transform the other public key with our loop size. So then our encryption key is we transform the card public key with our door loop size and print that. Let's just see if we can run that. Oop. Oh, gotta return num. Yep, I need in. Harry could have got that, but he's probably busy with his own solution. And submitted, correct. Just curious about the leaderboard on this one. Not that I think I made it. Oh, nice. That's pretty awesome. So people solved part 2 in 7 minutes. So whatever this is, might be short and sweet. Part 2, light turns green, unlocks. It's an emergency. The soft serve machine, glad that that's a Wikipedia link, of course. In the cafeteria on sub-basement 7 just failed, and you're the only one that knows how to fix it. Oh, wait a minute. Whoa. There is no part 2? Already dispatched a reindeer to your location to pick you up. Hey, I did it. As you fix the soft serve machine, Santa offers you a ride in his sleigh. Maybe the resort has a chimney you can use. Congratulations, you finished. I hope you had as much fun solving them. Love to hear about it. Supporting Advent of Code. That's an idea. Oh, there's Easter eggs. Huh. So, nice. What a beautiful little... That was so short, so sweet. What a beautiful little, I guess, hurricane. I'm gonna read the flavor text from part 2 in full. The light turns green and the door unlocks. What does that? Huh, yeah. Nice. As you collapse onto the bed in your room, your pager goes off. It's an emergency, the elf calling you explains. The soft serve machine in the cafeteria on sub-basement 7 just failed, and you're the only one that knows how to fix it. We've already dispatched a reindeer to your location to pick you up. You hear the sound of hooves landing on your balcony. The reindeer carefully explores the contents of your room while you figure out how you're going to pay the 50 stars you owe the resort before you leave. Noticing that you look concerned, the reindeer wanders over to you. You see that it's carrying a small pouch. Sorry for the trouble, a note in the pouch reads. Sitting at the bottom of the pouch is a gold coin with a little picture of a starfish on it. Looks like you only needed 49 stars after all. Nice. That's pretty cool. I like how the whole picture filled in here. I don't know what I'm gonna do with this method here, but let's wrap it up. 15-minute stream. I think that's the shortest one I've done. All right, till next year.